Hi, chemistry students. Today we're going to be learning about periodic trends. For today's activities, you're going to need some paper to take some notes and some pencils or maybe colored pencils to write with. It would really be beneficial for you if you had some paper copies of blank periodic tables. So I have one here. This is approximately what you're going to need. So if you want to sketch a few of these in your notes, right now you can do that. Now would be a good time to pause the video, sketch a couple blank periodic tables, and then go grab some paper for notes and something to write with, and maybe some colorful stuff. Get out your art supplies today. All right, so I assume you've paused the video and you're ready to move on. You got your stuff. Here we go. Mendeleev was a Russian scientist who had learned about a bunch of elements, and he was trying to explain how the elements were related to each other while he was teaching his students. And he decided, okay, the best way to make this logical for my students to learn is to write information about each element on a card. And then he arranged them by atomic mass. So he had a big long string of cards all laid out. And then he started to notice some trends. Approximately every 8 elements, they had some similar properties. And on each of the cards, it had things like how many atoms of hydrogen it bonds with, and what's its melting point and boiling point, and a bunch of properties of the elements. And he noticed these trends, and he started to arrange the cards in a table format. And it was pretty similar to the table that we use today. Here's a picture of Dmitri Mendeleev. He and Lothar Meyer published periodic tables in the same year, 1869, and they were the first periodic tables ever published. Some students think it's really surprising that they published at the approximately same time, but it kind of makes sense. All scientists at this point were really trying to understand how the elements relate to each other and how these trends work. They both published similar things, and they were both based on the physical and chemical properties of the elements, but Mendeleev is the one who's famous for this process. The reason is that he's so famous is because he made some really interesting predictions. At the time, there were a couple of elements, I'll try to show you here, germanium, GE right there, had not been discovered. And also, let's see, germanium and, I forget the other one. Tellurium, maybe? Anyway, so he had a couple of elements that were just spots, just blank holes on the periodic table that he put together. And he said, I think there should be an element that goes there. But not only that, he made predictions of their properties. So in 1871, he published this prediction about the element that later became known as germanium. He said, I think its atomic weight is going to be about 72, and its density about 5.5. Its color will be dirty gray. It'll bond with 2 oxygen atoms. And when it does that, the density of that compound will be 4.7 grams per cubic centimeter. It bonds with 4 chlorine atoms, and when it does that, it has a boiling point below 100, and the density of that compound is going to be about 1.9. And he didn't discover this element. Somebody else did, and that person was from Germany, and so they named it germanium, and they discovered it in 1886. And when they observed it, they made a bunch of measurements about it. What is its atomic weight? What is its density? And here are what they found. The density was 72.6. I'm sorry, the atomic weight was 72.6. Density was 5.47. The color was grayish white. It did bond with 2 oxygen atoms and had a 4.703 density. It did bond with 4 chlorine atoms, and its boiling point was 86. And the density of that compound was 1.887. So everybody was really impressed that Mendeleev had made these really precise predictions, and they turned out to be right. But really, it's not all that impressive, because what he actually did was he took the periodic table and said, okay, here's germanium. I'm going to average the atomic weight of the element above and below and left and right. I'm going to average those atomic weights, and whatever I get, that's my prediction. And he averaged the densities for the compounds near it. He noticed that germanium was in the same column as silicon and carbon like to bond with 2 oxygens each and 2 chlorines each. And so he used that information to make these predictions, and they turned out to be very, very precise and impressive. And so that's why he's well known. So it pays to make good predictions. So these trends are based mostly on the location of electrons. Remember, protons and neutrons are in the nucleus. Electrons are going around the outside. And Niels Bohr, you might remember, discovered that they were in rings or in orbitals. We call them orbitals around the nucleus. We now know a lot about where electrons are likely to be located, but there are some general rules. And because of the strange COVID situation, we're a little bit behind on our schedule this year. And so we are cutting back some of the details about where electrons are located. So when you take a college chemistry class, you'll have to learn a bit extra, maybe second semester. We'll get into it if we have time. So the general rules that you need to know, and these are the absolute minimum that you need to know, definitely write this down, is as follows. Energy level 1, that is the closest ring to the nucleus. Energy level 1, 2, 3, 4. There can be up to 7 energy levels, generally speaking, but sometimes you even have electrons occupying energy levels beyond energy level 7. Anyway, energy level 1 can hold 2 electrons. So I'm going to put my 2 electrons in there. Again, I want to point out electrons are tiny compared to protons and neutrons, so these electrons are not to scale. But to make them show up, had to make them a little bigger. So energy level 1 can only hold 2 electrons. Energy level 2 can hold up to 8, and they tend to pair up. So I've got 1, 2, 3, 4, 5, 6, 7, 8. Energy level 3 can hold up to 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And that's a sort of, because actually once you get beyond the 3rd energy level, some things get a little bit strange. We're not going to get too much into that this year, I don't think. But the most important electrons are the ones that are farthest from the nucleus, because they're the ones that can be involved in bonding. They're called valence electrons. So valence electrons are the ones that determine the bonding behavior of an atom. They're the ones in the outermost energy level of an atom. So if an atom has 3 energy levels, then it's going to be the 3rd energy level. But if an atom only has electrons in 2 energy levels, then the 2nd energy level is the valence energy level. These follow a trend on the periodic table. Here's where you're going to need those blank periodic tables. Hopefully you've sketched one up. If not, pause the video and sketch one right now. The trend looks like this. In the first column on the periodic table, all of those elements have 1 valence electron. All of these have 2. All of these over here have 3. Notice we skipped a big chunk. These have 4, 5, 6, 7. All of these have 8 with one exception, that is helium. Helium only has 2 valence electrons. And this section in the middle, which we call the D and the F block, F is down here at the bottom, these guys only have 2 valence electrons. So let's play a little game. Get your periodic table handy. Pause the video if you need to. And how many valence electrons are there in an atom of carbon? Carbon is in the 2nd row, over to the right, toward the top. Carbon atoms have 4 valence electrons. Did you get it right? And how about calcium? Calcium's element number 20. On the left-hand side, 2nd column, 4th row down. Calcium has 2 valence electrons. So memorizing that rule is going to be really helpful for your next test. So you can take valence electrons and make what we call an electron dot notation or a Lewis dot structure. Sometimes we call it a Lewis dot diagram. If you see the word dot, you know you should be drawing some dots. So electron dot diagrams are really simple to draw. You just find the symbol of the element and then you draw the number of valence electrons around it that it should have. So carbon has 4 valence electrons, so it's a C with a dot on the top, bottom, left, and right. Now they do pair up if there's more than 4. So with argon, argon has 8 valence electrons. It's on the far right-hand side, 3rd row down. And so it's going to have 2 electrons on the top, 2 on the bottom, 2 on the left, 2 on the right. Sodium has 1 valence electron, so 1 dot. You could put it on any of the 4 sides. I happen to choose the right side here. It doesn't matter so much. And chlorine has 7 valence electrons, so that's 3 pairs of dots. I put it left, right, and bottom on this one. And then 1 single dot, and I happen to put it on the top. The single dot could go any of the 4 sides. So learning to draw those Lewis dot diagrams will be very helpful. You might even remember this from middle school, where you learn how to make molecules and put together molecules that actually work based on those Lewis dot diagrams. And you should notice the dots are similar to the group number. If you look on your periodic table, you're generally going to see numbers across the top. Those are what we call the group number. And so, for example, argon was in, had 8 valence electrons, and it's in group 18. Here you go. And it's also sometimes called group 8A. Same thing, but yeah, that can be helpful to remember the numbers. Some other things you need to know about the periodic table are some real specific names for parts of the table. So vertical columns on the table are called groups or families. Verticals this way, right? Horizontal rows this way are called periods. So look at your periodic table. How many periods are there? Correct answer there is 7. There are 7 periods. These 2 guys down here actually belong in here, in between. So this is actually part of period 6, and this is part of period 7. The reason we pull them out and put them at the bottom is to make them fit nicely on a piece of paper. So how many groups are there? Group, again, is the vertical columns. So there are 18 groups. How many families? Well, group and family means the same thing, so 18 families as well. So here's a little quiz for you. To which family number does boron belong? Family. And boron is element number 5. Top right of your periodic table. And so it belongs to family number 13 or 3A. Either one would be an acceptable answer, but you should be familiar with both. Okay, to which period does chromium belong? Chromium is element 24. It's in that middle chunk, and it belongs to period number 4. And to which group number does magnesium belong? Magnesium is element 12. Don't get it confused with manganese, which is 25. Magnesium number 12 is in group number 2. And uranium, we're trying to put the family number on uranium here, but uranium is down here. And if you recall, we said that means it belongs in row 7, but it belongs in here, which puts it between group number 2 and group number 3. Well, that was a trick question. I wouldn't ask you that on a test. Some of the families have specific names that you need to know. So the alkali metals are the first family, group number 1, minus hydrogen. Hydrogen's a gas, so it's not a metal. It doesn't behave like a metal. It's kind of a weird element. So the alkali metals. And then the second column is called the alkaline earth metals. The second to last group over here is called the halogens. And the final column is called the noble gases. And you need to know those names. And some of the big chunks on the periodic table have special names as well that you need to know. So hopefully you've got a blank sketch of a periodic table that you can write this stuff in. These 2 sections of the periodic table are known as the transition metals or transition elements. They're all metals. These 2 groups are called the main group elements or the representative elements. Either one of those names will work. All of these elements over here, hydrogen, and all of these over here, those guys, are nonmetals. And you probably already knew that for some of these, like helium and oxygen are obviously not metals. But the rest of them being all grouped together, you should be able to locate those. So for example, I could ask you a test question like, chlorine, is it a metal or a nonmetal? And you would say it's a nonmetal just by looking it up on your periodic table. All of these elements are metals. I didn't get real specific with that squiggly line over with boron and silicon and such. And then these elements here are known as metalloids or semimetals or semiconductors. These elements have properties of both. So they're somewhat metallic, somewhat non-metallic. So metallic properties would be things like being shiny, being a solid at room temperature, conducting electricity. So these elements will do some of those things or do them kind of well, but not so well as the others. All right, then there are a group of elements that are known as the diatomic elements. These always exist in bonded pairs, so you would never write them alone. So like you'd never write an oxygen atom just O by itself in a chemical reaction. You'd always write O2. You're probably familiar with O2 for oxygen. So you got nitrogen and oxygen. You've got all these over here. Remember, those are the halogens. And then hydrogen, being weird, over there as well. So if you look at these, it happens to be all the ones that end in gen, hydrogen, oxygen, nitrogen, and then the halogens all end in -ene. So the gens and the enes are your diatomic elements. There's also a trend on the periodic table about the size of the atoms. And as you're going down the rows, it kind of makes sense because as the atoms get heavier, they also get physically larger in radius. But as you move from left to right on the periodic table, the atoms actually get smaller even though they get heavier, which is kind of strange. And so that's a rule that you'll want to memorize. That the bottom left is the largest atomic radius and the top right is the smallest. So I try to remember francium is fat. So they kind of sound, they start with the same first letter. Francium is fat. And helium, if you breathe in helium, it makes your voice sound all tiny, right? It's the tiniest element. So atoms get smaller to the right and smaller as you go up. Francium is fat, helium is tiny. And there you go. So hopefully you got all of that. If not, please go back and rewind through the video and watch the sections that you need to see again. And we've got a quick little quiz. It's kind of a fun little challenge. So give it a shot and see how it goes and do that on Schoology. And that's how I'll check to make sure that you were in attendance today. If you have any questions, I will be around. So send me some messages. If we need to Zoom, we can do that. Talk to you later.